So today's session is going to be a really special one because it is going to be co-hosted by myself and my colleague, John Dow. We worked on the content of this presentation together. John, do you want to go ahead and introduce yourself?
Yes, my name is John. I'm the applications engineer at KETIV. I specialize in the structure side. Thank you, Snigdha.
Absolutely. And John, thank you so much for helping me put together the content of this presentation. So getting started with the agenda today. Today's demonstration and the content is geared towards exploring Ansys capabilities for optimization, parametric study, and just improving your designs overall. We're going to be doing a demonstration in which we'll set up some input parameters. These will be both geometry parameters and simulation parameters, and we'll vary these to see what kind of impact it'll have on our output or quantities of interest. The example that we've chosen for the demonstration is very interesting, something that we haven't done before. It'll be a one-way coupled fluid and structure simulation. We're going to be doing one-way FSI and transferring our output from the CFD simulation to the FEA simulation. So that's going to be really interesting as well. Now, before I jump into the demonstration, I want to talk a little bit about the relevance of this topic and, why as engineers or designers or even analysts, one should care about design exploration or optimization to begin with. I know from personal experience in the industry that a lot of engineering teams, they rely on established practices, established workflows or legacy designs, to keep developing the similar designs in the future for their products because they simply don't have the bandwidth, the extra resources, time to, come up with the best possible design. So today you might have a design that meets your design goal, your constraints, your objectives. Maybe you have a high factor of safety, but is that the best that you can do? Can you optimize it further? Can you perhaps lightweight it? Maybe that'll reduce the cost of production. Maybe that'll reduce the time to market. So these are some of the questions that engineering teams, don't really always have the luxury to explore. And that is where, Ansys can come in and fill in those gaps for you, wherein it'll take the burden of doing these, explorations and hidden trials, and, let you come up with the best possible solution that will eventually lead to a reduction of resources that goes in for your product design. If you want to study the impact of changing your geometry or operating conditions and see how your output changes, maybe you're doing some sort of a research, maybe you're relying too much on experimental data. That is, again, an area where Ansys design exploration can really help you. Right? You can reduce the number of simulation steps that you would have to do in a tedious fashion for each and every iteration of yours, and instead rely on these features and capabilities that Ansys has to offer when it comes to parametric studies or, optimization, right? Overall, all these reasons contribute to, making your engineering workflow a lot more complicated than it needs to be. If you can take away from the time and the cost and the manpower that goes behind coming up with the best possible design, then, I'm sure it'll pique your interest and, improve your overall workflow. Having said that, what are some of the features and capabilities that Ansys has to offer in terms of Design Explorer or even Ansys Workbench? Now, I know that we have done some sessions in the past wherein John has gone over, these features in detail, but just for a quick recap before we go into the demonstration, I wanted to re-highlight some of those capabilities that are available to you. One, obviously starting from the basics, you can explore multiple designs quickly. You can do a parametric study wherein changing your input parameters will help you quickly assess what kind of impact you'll have on your output. You could also do design of experiments to actually reduce the number of experiments you'll have to physically perform to establish a relation between your input and output. So there's always the cost saving aspect in doing something of this sort. You could also do parameter correlation, wherein you could understand how sensitive your output quantities are to your input parameters, which parameters are important for consideration while coming up with the design of future products, similar to the one that you're designing right now, and which parameters don't really make that much of an impact, right? And then, of course, you can use your DOE to generate a response surface to get the best fit curve. This is not, as time consuming as setting up a DOE because you get your results instantaneously. It's based on the meta model that is generated depending on the design points that you've already solved. And again, you could make all these optimization activities goal oriented. You could, set a certain amount of stress under which you'd like your design to be, a certain amount of pressure, anything, that you would use as a physical design goal while coming up with your product design can be likewise translated to the simulation or Ansys, work frame, and you can optimize based on that particular set goal. So really cool features that one should definitely think about and explore. If you have questions about how DesignXplorer or Ansys Workbench can apply to your own application, or maybe you already have Ansys but are not using it today to do any sort of optimization, please feel free to reach out to us. We'll be happy to help in whatever capacity we can. We'd love to learn a little bit more about your applications and figure out how Ansys can fit in the picture and make your job easier for you. So let's just talk about the problem statement for a bit. So this is the problem statement for the demonstration that we will be covering. This is a very simple nozzle design that John came up with. And what we have here is, water coming in and out of the nozzle. The material of the nozzle is plastic because we wanted to, just highlight the kind of impact fluid pressure can have on such a material. And what we're going to do is we're going to do a fluid simulation and get the fluid pressure on the walls of this nozzle, and then transfer it over to the structure side of things, wherein we will be monitoring certain quantities of interest. John, do you want to talk about, what we do on the structure side?
Yes, so we're going to be studying how, as you know, for an inlet and outlet, if you vary the diameters, you're going to have a different velocity. So in this nozzle, the only diameter that will be changing is the outlet diameter. So by closing that up, we're going to be increasing the velocity. And what does that do? That's going to introduce a force onto the nozzle, because it's going to be spraying with all that kinetic energy that's coming out from the water, right? That's spraying out. So in turn, what that's going to do is it's going to cause a stress on this nozzle. So for myself as a mechanical engineer, that's some pretty interesting parameters I can collect from a CFD engineer, because I'm not aware of what type of pressures I'm going to be getting from these flows and how it's going to affect my nozzle. So this is what the FSI is going to be, the fluid structures interaction. It's going to be the fluid flow through this nozzle causing a stress from the velocity, the changes from closing up that diameter.
Absolutely. And as output quantities, or quantities of interest, we're going to be monitoring the stress and deformation on the nozzle due to this fluid pressure. So we have certain input parameters that we'll be varying, including the flow velocity and the geometric parameters such as the outlet diameter and thickness. And then for outlet parameters, we'll be looking at maximum stress and deformation, right? So this is what the demonstration results will look like. You're applying a certain force on the inner walls of the nozzle, and that will cause some amount of stress. So it's going to be a really interesting, simple but effective little workflow to highlight how this one-way FSI can be done, right? So with that, let me switch over to the demo and let me share a new screen. Okay. Can you guys see the video, JD? John?
Sorry, I was on mute. Yes, yes, we can see the video.
Awesome.
Sorry about
Awesome.
that.
You good. Awesome. So what you see on the screen here is the Ansys workbench. This is 2020 R2. And we're going to be starting off with the fluid analysis first. So this is already pre-recorded because there are a lot of, small steps. So if you have any questions, feel free to, enter it in the Q&A box, and I can stop at that point and talk a little bit more about the step that I'm currently at. So I'm going to go ahead and play it, and I'm going to talk through the demonstration as and when me and JD complete the steps. So initially what we did was we dragged and dropped the fluid flow analysis system from the analysis system onto our project schematic. And we're going to go step by step from geometry, mesh setup, etc., to make sure that we have all the cells in order. So what you see on the screen here is the geometry part. Now this is in Inventor, and the idea of setting up the geometric parameters in your CAD tool is very well highlighted. You can see John setting up those outlet diameter parameters within Inventor. You could do these same steps in whatever CAD tool you're using right now. I, for example, do not have Inventor, so I would do this step in SpaceClaim. But if you're using SolidWorks or any other tool, you could directly import the geometry parameters from that CAD tool into Ansys Workbench. And what happens is when it comes over to your prep tool, for example, if you import it inside SpaceClaim, you should automatically be able to see those constraints. Now, keep in mind that sometimes, you need a separate CAD interface for these parameters to carry over. So that is something that you would have to check on your end, whether or not you have or need a CAD interface to get those parameters. If not, then you can recreate it within SpaceClaim itself. So I'm going to stop right here, and on the right you can see that the parameters that John set up in Inventor have been carried over within SpaceClaim. So this was really easy to do. And then what we'll do is we'll just do a simple volume extract within SpaceClaim to get our fluid volume for the CFD analysis. So you can see that the gray volume has been created internally. And again, these are like really simple, very intuitive features that you can access within Ansys. And although
Hey,
the
Snigdha.
Yes, John.
That's something I wanted to highlight that's interesting about that fluid volume. When you change the parameters, let's say if I change the diameter of the outlet, it actually updates that volume extraction, correct?
Right.
That's what's nice about SpaceClaim. That's what I really like about it.
Yes, absolutely.
you don't have to repeat those steps over again. It just updates on its own.
Absolutely. And we're now in the Ansys meshing framework to set up the mesh for our fluid analysis. And here we'll make sure that we choose the fluid volume. Because for the CFD analysis, I don't really need the walls of the nozzle. I can just concentrate on the internal fluid domain, and that should be enough to get the fluid pressure on the walls. Now, for the purpose of this demonstration, we didn't pay a lot of attention to the, mesh accuracy and how refined it should be. But, if you're setting up an actual case where you're really interested in the values, or, you're doing research, make sure that the CFD mesh is good enough and captures all the finer details of the geometry. And here we're setting up the inflation layers. At the walls. John, do we have any questions in the meanwhile?
Let me take a look. No, not right now.
So what you can see is a fairly coarse TET mesh that has been generated on this fluid volume over here, right? So we're going to make it a little bit finer. And once the mesh part is done, you will see a green check against cell A3, and then we carry this over to the fluent side of things, where we'll actually set up the flow through the nozzle. Now, for the sake of, saving time, I edited out the part wherein, we created named selections within Ansys meshing to denote the inlets and outlets. So you can see the inlet and outlet specified in blue and red respectively. But you could do this within SpaceClaim itself. And here I'm just setting up a simple water flow simulation with an inlet velocity and a pressure outlet. Just checking that the fluid domain is correct. And changing the material from air to water. I'm going to keep the properties as it is for incompressible flow, just the density and viscosity. And make sure you have the correct material specified in the cell zone.
Hey, Cindy, we had one question that maybe can be answered right now. Someone asked about, is this a good use case for mosaic meshing?
So that is a very good question. Let me stop the video so that I can answer the question. So in Ansys Fluent Meshing, as of today, if you use the watertight geometry meshing, you can import external CAD parameters. In this case, it has come from our Inventor tool. So for the sake of this demonstration, I'm just, using Ansys meshing so that those CAD parameters, transfer over. But you can always use, Fluent meshing for parameters that you set up internally within the Ansys workbench. So mosaic meshing right now is not available within Ansys meshing. It's only available within Fluent meshing. So that would not work for this demonstration case. So I hope that answers the question, and I'll resume the video over here. So we're entering a velocity magnitude at the inlet, and take note of the fact that, I didn't keep it as a constant, but I specified this inlet velocity value as an input parameter. So the moment I click on parameter, it asks me to come and look at the nominal value here and perhaps assign a name for this parameter that I can later use in my design study. So I'm going to name it as inlet velocity. And at the bottom, you can see it says use as input parameter. And I'll just hit OK. And then for the outlet, we're just maintaining zero gauge pressure. And this is not going to be a parameter. I just kept it as it is. Now, this wall is very important because in this coupled FSI simulation, this is the surface on which, we'll be mapping fluid pressure onto the structure side of things. So for the sake of clarity, I renamed the wall as the FSI wall so that later on when we're doing the FE analysis, we know which surface to select. This could be helpful if you have a complicated geometry where, you have a lot of surfaces. So you could easily set it up as something that is clear later on. Now, if you were to do a simple CFD analysis and set up some output parameters, this is where you would do it. You could simply come to report definitions within Fluent and click on create output parameter at the very bottom. For example, right now we are looking at the force in X direction on this wall, which I've named as Fx. And I have checked the box at the very bottom, which creates an output parameter for this variable. Now you could also set up these output parameters in CFD post if you were to use CFD post for your post processing. So that again is an option, but just for the sake of simplicity, I'm doing everything within Fluent itself right now. The convergence tolerance is not reached, but that's okay. We didn't really pay much attention to the mesh, and I'm not even sure if I used some other settings. So you can see that, the iterations run smoothly. Like I said, this is a simple case, doesn't really need a lot of hit and trial. We have specified a certain number of iterations after which it will stop, even though the convergence criteria has not been met, but the variables or output parameters have steadied out. So just for the sake of demonstration, this is good enough. And you can look at the force values as well. So this is nearly around 2.8 pounds in the X direction. And then you have a certain velocity at the outlet. Keep in mind that the outlet diameter was smaller than the inlet diameter, so you can see that increase in velocity accordingly. So now, when we come back to Workbench, we see that all the upstream cells have a green tick. And I'm just going to pause right here because this step was a little fast. So what we did was simply drag and drop a static structural analysis onto the solution cell, which is cell A5 of the CFD setup. What that does is it automatically creates a connection between the solution from CFD to the setup on the FEA side, right? And this link is important because we're going to be mapping the fluid pressure as an input load for our FEA analysis. And once you do establish that connection, the geometry part is automatically carried over. So we're going into John's territory from this point forward.
Feel free to forward the video of Snigda if you want to. Just I don't.
Yeah. Do you want to talk about this, JD, or I can, do some overview description?
Yeah, sure. So over here we brought in the nozzle. You can see that the volume was imported as well. So I ended up suppressing that because we're not interested in that part of the simulation. We're just interested in the plastic nozzle itself. And we're going to assign a plastic material to the nozzle. And for the sake of this simulation, we're just going to auto mesh it. We're not going to, the whole point of this is for us to cover the DOE part of it. And here's the interesting part. So since we linked a Fluent solver over, we get a new option here, and it says import load. And you can see that on the left side, it's A5. And here I get to import the loads from Snigda's Fluent simulation.
So you can see, John, selecting those same walls that I named as FSI wall on the CFD side of things, because that is the wall that is common to both these simulations, and that is where the pressure values will be imported. So you can see that the FSI wall automatically shows up in the CFD surface. And when we click on imported load, we get a green check. And John, we're setting up stress and deformation here.
Correct.
I have always been envious of how little time it takes for structural simulations as compared to CFD simulations.
Yeah, I too appreciate that.
So this
okay, so
cool. Go ahead, JD. I'm sorry.
Oh, no problem. No. You're good. So this is just based off of the first diameter. So what I'm doing now is setting some parameters, output parameters. So before we had input parameters, that's the things that we're going to change. We have control over. Now the next set of parameters I just set was for the stress and for the deformation. And those are going to be like a cause and effect, right? So whatever parameters we change in the sense of the geometry. Let me just review real quick. We set a few things on the geometry. One, I set a parameter for the radius because I can see that there's a high level of stress in that radius. So if we can control that radius, is it going to reduce the stress? The second parameter I changed was the thickness of the nozzle itself. How does that affect the stress? And finally, I set a parameter on the outlet diameter, and we're interested in how that can increase the force from the CFD simulation, and therefore apply a load on our nozzle. Okay.
Let's see.
Yeah, we could continue the video.
So once we have this part done, I think John just updates everything upstream of the results. So you can see, this was really easy and intuitive, just, dragging and dropping some analysis systems onto Workbench and easily be able to do a multi-physics simulation. If you are working with such applications and, you've always wondered about being able to connect your CFD structural or, electromagnetic simulations, then definitely Ansys Workbench is one of the more convenient and easy to get up to speed with tools out there. So hopefully that was of interest, and we're going to move ahead to the setting up of parameters. Now, I just want to, pause the video over here and, talk about something very important, I think, is that, if you're just doing a parametric study, if you don't want to do a design exploration, if you're simply doing a what-if study wherein you're changing one parameter and seeing how it impacts your output parameter, then you don't even need to, do the design of experiments. You could just simply do that in Workbench. And depending on your, hardware resources, you should be able to get your answers accordingly, right? If you want to run multiple design points at the same time, then, you would need that additional license, that additional, hardware. So if you have questions about that, or if you're wondering how Ansys can help you in that direction, please feel free to reach out to us. We'll be happy to discuss it with you. But for simply doing what-if studies as a first step, you could do that even without the DOE part. In this case, what John did was he just, dragged and dropped the design exploration part onto the project schematic. And then, we're gonna work through the design points and see how that is set up. So that is a little bit more advanced, a little bit more advanced capability that you can leverage. But yeah, just wanted to mention that for anybody who's getting started with optimization or parametric analysis. So on the left over here, you see all the input parameters that we have set in. If you remember right from the very beginning, DSD1, DSD2, the radius, the thickness, these were all geometry parameters that John set up. And then the last one, P5, which is inlet velocity, that one was set up in Fluent, where we could just, vary it based on whichever operating condition we want to evaluate our results at, right? And then we set up some output parameters, some in Fluent, which was the force in the X direction and the velocity outlet. And then on the structure side, we are looking at the maximum stress and the minimum deformation. So when you click on design of experiments, you can see the lower and upper bounds of all these, geometric constraints. And these constraints might be important for you, when you're actually designing a product, it has to be manufacturable. So you might already know these geometric constraints that you would like to, employ on your design study even before you start with the design exploration. So once you set up your DOE, what Design Explorer does is it automatically comes up with all the design points that you would need to fill up your design space. What that means is these are the minimum recommended number of design point entries that you would require to establish a relationship or trends between your input parameters and output parameters. So if you were to choose less number of design points, say suppose just 5 or 6, maybe those wouldn't be enough for you to establish any kind of trend or relationship, and you wouldn't understand how one parameter is impacting your output results. Isn't that correct, John?
Correct. Yep. Precisely. So, Sunita, did you want me to take over from here and share my screen?
There is still a little bit left, John, but if you want to talk
sure.
portion, please feel free to jump in. So what John is basically doing is he's just going to go ahead and update this table that you see over here. And in doing so, what Ansys is doing is it is solving all these design points and coming up with a solid, background to generate a surface response. And after this, I'm going to let John share his screen because he can show you real time what the response looks like, or what sort of values we can derive from this exercise. So I'm going to go ahead and stop sharing the screen. John, do you want to go ahead and share yours?
Yes. Yeah. Let me take over. If I can find the Zoom window. Okay, here it is. Okay, so okay, can you see my screen, Snigdha?
Yes, I can see it.
Okay, so I'm carrying out I'm taking over and carrying off where we left off on the video. It took approximately I believe it was like a 1.5 or 2 hours to solve this design of experiment. So if you're gonna be doing design of experiments, it's probably good to do this overnight, or if you're gonna go to lunch or after hours, because it does take a while. Because what it is doing is it's actually changing the geometry for these parameters that are set here, for these geometry. Like you can see, there's different dimensions for the diameters, and then there's different dimensions for the radius, and there's different dimensions for the thickness of the nozzle itself. So what it's doing is it actually goes into the geometry, changes it, and then it's going to import it into Fluent, and then it's going to solve Fluent, and then it's going to export that out into mechanical. It's going to do the whole thing that we just did right now, and it's going to do that 29 times, and it's going to solve for each one of those. And from there, we actually get results. So you can see from Fluent, Snigdha previously parameterized the force that from the nozzle, and this is in newtons, by the way. And you could also see the velocity. So as the force increases, you can see it's obvious the velocities, it's because the velocity is higher. And we also have stress results and directional deformation. So that's nice. We solved 29 different cases. And from here, these are set in the parameter set. So like Snigdha was saying earlier, if you weren't using Design Explorer, you could actually hop into, let me go back to the GUI. So from here, if you double click on parameter set, you could type in whatever parameter sets you're interested to solve for yourself and get these results. But we're using Design Explorer, which automated some of this data for us, because Design Explorer is collecting this data so that it can give us information. And I'm gonna move a little quicker on here because we actually have previous videos that I made on Design Explorer where we did design of experiments. The purpose of this was just to show you this design of experiments being done with fluent and mechanical, as well as an FSI, fluid structures interaction simulation. So from here, I can actually go over to response surface, and I could take a look at information from what I just collected. So the parameters here are the diameter, the radius, and the thickness. And we can see what affects the stress the most and what affects what out of these three geometry parameters, which one's affecting the stress the most and which one's affecting the directional deformation. And it turns out that the diameter of the nozzle it's quite obvious, because when we manipulate the diameter of the nozzle, we're increasing the velocity output of the liquid or the fluid. Sorry, the fluid. So that's why that one is such a large bar. The next one is the thickness. The thickness of the nozzle, it turns out, affects the stress more and the directional deformation more than that radius that we set a parameter to. So that's what these bars are telling us.
And this might be important, when you're thinking of designing, something new. You may want to understand, hey, which parameters will affect my design the most. That is how I will go about, focusing on such and such parameters, right? So
yes,
sensitivity part really comes into the picture when you're thinking about the overall design process.
and something else that's nice, since Ansys, after you solve your simulation with those design points, Ansys uses a statistical approach to see if it can create a trend that falls closely along the simulation results, which is the line, and then all these little, which are all these points and the lines. So if you see these points and lines, if they're pretty nice and fitted together, then that means you have some good data. They also rate that data over here in this table with all these stars. If you're interested, I give more details on this in my other AVAs, where I go over design of experiments and response surfaces. But I wanted to go over here to show that now that I have some of this data, I can actually just start typing in some numbers, and I'm actually getting some quick results. Now these are blue in color because these are approximations. They're not based off of the simulation. It's based off of the statistical approach that we just collected. So if I 0.08 and if I do 0.07, I'm already getting, oh, that's not within the range that we set earlier. So I'll just 0.06. And you can see I'm already getting some results over here. And that's pretty quick. And the next interesting part is the optimization. So I know it's already 10:50, but this is where you would want to set some parameters, such as what if I wanted to put the diameter, I wanted to minimize, let me see, the force. So what if I wanted to actually this one's not a good one. Let me remove this one. What if I wanted to reduce the force the most? I could minimize that as a constraint. And I want to reduce velocity and stress. Date. So if I were to apply some optimizations here, it would give me some results, and it would find the best geometry parameters that would satisfy those needs. It might take a little time to solve, and I know we're running 10:50. We're almost running out of time. But over here, in the previous constraints I put, it would select the design candidates that best fit those constraints that I just applied. Try to hover my mouse over here, and it selects the best 3 candidates, and you could select, and you can see the results here. And then from here, you can actually import this into the parameter set and solve it in the simulation. And let me see if it's saved over here. And these are all saved in the parameter sets. And so if I were to right click and set this, series design point, let me see, set update row. I want to set this one as I want to set this as a simulation. Set as current. If I set this as the current, if I were to open the simulation, it would change the geometry. All the results here are from that parameter set. So actually I have 29 saved simulations essentially.
So you could go back to any design point and look at the results in detail, correct, JD?
Yes. Yeah, you could come and explore it. So you can see the diameter small. I believe when we first set this, the diameter was a larger diameter, but this one's smaller now.
Exactly. And the optimization can be done in real time, wherein Ansys is actually coming up with those design points to meet your set goal within the constraints that you've specified. Or it can also do optimization based on the response surface that you've created. That's going to be a lot faster because, again, it's based on a meta model and it's more statistical. You wouldn't have the simulation at your you won't have the simulation to access as such, but if you're looking for any quantities of interest, then that approximation can definitely be found with the help of DesignXplorer.
Yes. Yeah, I think this is probably one of the most useful, this table here that I'm playing with, because this is already giving me information rapidly. I can start just typing stuff in. You see over here, I changed the diameter from 0.1125 and I have it versus 0.1375. And you can see that the small diameter is creating a larger force and has more velocity. Of course, these are approximations, and I could also choose to insert this as a design point and solve it for a more accurate simulation. And these numbers will update and they'll become a black, which is means that they've been solved through the simulation. But right now, what's really nice is this this table just gets me results pretty quick. I could change the radius. Oh, what's the minimum here? Of course, these are limited to the bounds that we put earlier. So let me try to put 0.08, and let's see if that reduces the stress. I'm gonna increase the thickness, 0.068. Okay, hold on. 0.068 was the limit I put here. And let's take a look. Let's make sure we keep our eyes on G5 over here. Yep. Stress. It looks like the stress increased, huh? That's interesting. So what if I change the radius? Or decrease the radius?
That's the beauty of playing around with these parameters. They can affect your output individually, or depending on the application that you're solving, it might have some other effect, which is really the point of doing this design exploration, is to be able to test out those operating conditions or design parameters that you wouldn't have the bandwidth to explore if you were to do all this manually.
Right.
And
it takes a little thought up front. You have to think about what you want to do. So it does take people that have experience with simulations to think a little ahead so that they could set these up. but it saves a lot of time in the end. You could see that, okay, if I knew the 5 different things that might affect the stress of this, let me parameterize those. Let me do design experiments, and then let me study 20, 20, 30, 50 different type of designs.
JD, we have a question about displaying an actual response surface. Do you have it already exported for this case? I know you've shown it in your previous ABAs.
Displaying an actual response surface. Can you clarify that question?
So
Displaying an
like
actual response surface, you mean
the 3D graph that shows how the meta model predicts the values. I think if what the yes. So you already have it, and you can vary it depending on what kind of fit you're looking at, what kind of trends you're looking at, whether you're looking at.
yeah. Let me put back to 2D again. But yeah, let's say we have let's put that diameter again, and then let's have that velocity, right? Let's just put velocity, because we know the smaller the diameter, the higher the velocity. That's an obvious relationship there. And you can see that as the diameter increases, the velocity is going to decrease.
Right.
And what about stress? So I'm going to put a relationship with stress. So uh, the same thing's happening. It's a similar trend. As that velocity increases, the stress is going to increase. As that diameter is bigger, there's going to be less stress, because there's going to be less energy coming from the fluid flow.
Right. So basically, to answer the question, we can, choose a 2D response surface or a 3D response surface, and, vary the statistical analysis to get the best fit possible. Correct, JD?
Yes.
Okay. And I think there was another question about what if I had a geometry that did not have parameters in the first place? If it was made from an imported scanned object, how would we optimize that? I know for a fact that, Ansys has a lot of design tools available that have the option of topology optimization. If you don't already have parameters in your geometry, then we're going to be doing some Ansys discovery workshops in the future. Be sure to check those out. And I'm not sure if this is in line with your question, but
let me add to what you're saying, Snig. That just
yeah.
I believe. So if you have a geometry, as long as you can set features on that geometry, you could parameterize it. So if that's thickness, a radius, a hole, as long as you could set a feature to that geometry, you could parameterize it. In your case, you're asking if, let's say, if you 3D scan something, or if you did a topology and you got an STL file, you're going to have to do some work, and you're going to have to create your own geometry based off of that STL file. Of course, you could take the STL file, you could convert it over to solid, but because that's going to have a lot of surfacing on that geometry, we're not going to be able to grab a feature and apply a parameter to it, because a parameter does depend on a feature. So, Asad, I hope that answers your question there.
Yes, that is true in this case of DesignXplorer. But if they were to just, do a topology optimization with an Ansys discovery, they could, vary the geometry significantly in order to meet a certain design goal. But again, there are some constraints with that as well. And, we can discuss it in a future AVA. But yes, yeah. And let's see, I think there is this a quadratic model? I'm not sure, but I know that you can definitely do a quadratic model when you're looking at the response surface. So the one that JD had shown you a little while ago, I don't remember the settings to comment on whether or not that was quadratic, but Ansys gives you the capability of doing a quadratic fit for
there's
response surface. Yes.
If you're interested in learning more about DesignXplorer, there's a lot of good classes that you can take on the Ansys Learning Hub. And if you're interested in the Ansys Learning Hub, please contact us. Let us know. We can help you there.
Absolutely. So I think, we are coming up on the hour. JD, thank you so much for your help with, putting together the content and also presenting all this information to our audience today. Um, this was really interesting and something new that we did in our AVA sessions. So thank you, JD. Thanks. Bye-bye.
Thank you. All right, bye everybody.